What actually happens inside a CPU when it guesses wrong? A branch looks easy in code, an if loop, a conditional jump, but inside the processor, that single decision can trigger one of the most expensive mini-disasters in modern computing, a pipeline flush. And that flush happens because of something CPUs do constantly, that they predict the future. In this video, we're going to break down exactly what a pipeline flush is, why branch mispredictions happen, what gets thrown away, how the CPU recovers, and why this matters so much for performance. By the end, you'll be able to visualize the whole chain. Fetch, predict, execute, discover the guess was wrong, flush everything, restart, and keep going. Let's build that mental model from the ground up. First, the core problem. Modern CPUs are deeply pipelined. That means instruction execution is split into stages. A simplified pipeline might look like this: fetch, decode, rename, dispatch, execute, and retire. Different instructions are sitting in different stages at the same time. So while one instruction is executing, another is being decoded, another is being fetched, and another is retiring. This overlap is how CPUs go fast. Instead of finishing one instruction completely before starting the next, they keep many instructions in flight at once. That's the pipeline. Now, here's the problem. What happens when the CPU reaches a branch? For example, if this value is 0, jump over here. Otherwise, continue over there. The branch outcome is not always known immediately. The CPU may need to wait for a comparison result or for data from a previous instruction before it knows which path is correct. But the pipeline cannot just sit there doing nothing. If it waited at every branch, performance would collapse. So instead, the CPU makes an educated guess. This is called branch prediction. The processor predicts whether the branch will be taken or not taken, and it also predicts the target address if the branch jumps somewhere else. Then, based on that prediction, it keeps feeding the pipeline with instructions from the predicted path.
This is incredibly important.
Without branch prediction, deep pipelines would stall constantly. With good prediction, the CPU stays busy and keeps executing instructions at high speed. But prediction is still a guess. And when the guess is wrong, the CPU has a problem, because now the pipeline contains instructions from the wrong future. That is the key idea. A branch misprediction means the CPU speculatively fetched, decoded, and maybe even executed instructions that should never have happened on the real architectural path. Those instructions are not valid anymore. They belong to the wrong control flow. So the CPU has to get rid of them. That cleanup process is what we call a pipeline flush. Now, the phrase flush the pipeline can sound dramatic, like the CPU wipes everything and starts from absolute zero. But the reality is more specific. The CPU throws away the younger speculative work that depends on the wrong prediction. It preserves the older instructions that are still valid. To understand that clearly, let's walk through an example. Imagine we have a simple piece of code. Load a value, compare it to 0.
If equal, jump to label A.
Otherwise, continue to label B. Now, suppose the CPU predicts that the branch will not be taken. So it starts fetching instructions from the fall-through path, label B. Those instructions move through the pipeline. Some get decoded, some get renamed, some enter scheduling queues. Some may even begin execution speculatively. Meanwhile, the comparison instruction is still making its way through the machine. Eventually, the branch executes, and now the CPU finally learns the truth. Oops. The branch was actually supposed to be taken. That means the CPU should have gone to label A, not label B. Everything already in flight from label B is now on the wrong path. Those instructions must be cancelled. That cancellation is the flush. So what exactly gets flushed? In simple terms, all the younger instructions that entered the machine after the mispredicted branch, and only because of that wrong prediction. They may be sitting in the fetch queue.
They may be in decode.
They may be renamed. They may be waiting in reservation stations. They may even have partially executed. But if they are younger than the branch and they came from the wrong path, they are squashed. They will never retire. They will never update the architectural state. As far as the program is concerned, they never happened. That last part is extremely important. Modern CPUs use speculative execution, but they do it in a way that preserves the illusion of correct sequential program execution. Even if wrong path instructions executed internally, their results are treated as temporary until the CPU knows they belong to the correct path.
Architectural changes only become official when instructions retire in order.
So when a misprediction is detected, the CPU can discard the speculative results before they become visible to the program. That is how the processor stays correct. Now let's slow down and separate two ideas that often get mixed together. Executed does not necessarily mean committed. An instruction can execute speculatively and produce a temporary result. But unless it retires, that result is not part of the official machine state. That distinction is what makes branch prediction practical. The CPU can be aggressive internally while still guaranteeing correct external behavior.
So how does the CPU know what to roll back to?
This is where structures like the reorder buffer become critical. And out-of-order CPUs do not just execute instructions and immediately commit them. Instead, they track in-flight instructions in program order. Results are held speculatively until the CPU is sure they are safe to retire. The reorder buffer or similar machinery helps the CPU remember which instructions are older, which are younger, which have completed, and where the correct retirement boundary is. When the mispredicted branch resolves, the CPU identifies that branch in its in-flight window. Everything younger than it is invalidated. Their entries are removed or marked cancelled. Their temporary destinations are discarded. Their scheduler slots can be reclaimed. Their loads, ALU ops and other speculative work are abandoned from the architectural point of view. Then the front end is redirected to the correct target. That means instruction fetch stops pulling from the wrong path and starts fetching from the right one. This is the recovery phase. So the recovery process looks like this. First, detect the branch was mispredicted. Second, squash younger wrong path instructions. Third, redirect fetch to the correct program counter. Fourth, refill the pipeline with instructions from the real path. That's the full loop. Predict, speculate, discover, flush, recover. Now, why is this expensive? Because a misprediction wastes work in two different ways. First, the CPU spent cycles fetching, decoding, scheduling, and maybe executing instructions that turned out to be useless. Second, once those instructions are flushed, the pipeline needs time to refill from the correct path. During that refill period, the CPU is not making as much forward progress as it normally would. That lost time is called the misprediction penalty. The exact penalty depends on the CPU design. On a shallow pipeline, it may be modest. On a deep, wide, high-performance core, it can be very costly.
Why?
Because deeper pipelines mean more distance between branch prediction and branch resolution, and wider machines can have more wrong path instructions in flight at the moment the branch finally resolves. So a single bad prediction can waste a surprising amount of machine bandwidth. This is one reason branch prediction is such a huge deal in CPU architecture. A fast CPU is not just about higher clock speed. It is also about keeping the pipeline full of useful work. And branch prediction is one of the systems that decides whether the work in the pipeline is useful or garbage. Now let's make the intuition more concrete with an analogy. Imagine an airport moving walkway with workers placing boxes onto carts. Each box is an instruction. Each worker station is a pipeline stage. Everything runs smoothly as long as the workers know which line of carts should receive the next boxes. Now imagine there's a fork in the route ahead, but the sign telling you which way to go hasn't been revealed yet. Instead of waiting, the workers guess probably left. So they keep loading boxes onto carts, heading left. A few seconds later, the real sign appears. It says right. Now all the boxes loaded for the left path are wrong. They have to be removed from the line, the carts have to be redirected, and the workers need time to start filling the correct route. That's a pipeline flush.
The machine didn't break.
It just invested work into the wrong future and now has to rewind to the last known correct point. Let's also address a subtle but important question. Does the CPU literally erase everything? Not exactly. Older instructions that came before the branch and are still valid do not get thrown away just because the branch was mispredicted. The CPU only squashes the speculative state that depends on the wrong path. This selective rollback is what makes modern CPUs efficient. They are not resetting the whole core. They are surgically removing the bad speculation. Another subtle point. Not every control flow disruption is the same. A branch misprediction is one common cause of a flush, but other events can trigger similar recovery behavior too. For example, exceptions, interrupts, memory ordering violations, or certain machine clears can force the processor to discard speculative work and restart from a known good point. So flush is part of a larger family of recovery mechanisms but branch mispredictions are the classic example and the easiest way to understand the concept. Now let's connect this back to software. Why should a programmer care? Because branch-heavy code can be much slower when predictions are poor. If a branch is highly predictable, for example, it almost always goes the same way. The predictor learns that pattern and the CPU stays efficient. But if the branch is random or depends on unpredictable data, the predictor will miss more often. And each miss can trigger a flush. That means more wasted work, more front-end redirection, and fewer useful instructions retiring per cycle. This is why the same algorithm can behave very differently depending on data patterns. And it's why low-level performance work often talks about branch predictability, control flow regularity, and branchless techniques. The goal is not just reducing the number of instructions, it's reducing pipeline disruption. A well-predicted branch is cheap. A badly predicted branch can be very expensive. Now, let's zoom in on the timeline of a misprediction. Cycle 1, the CPU fetches a branch. Cycle 2, the branch predictor makes a guess and fetch continues down that predicted path. Over the next several cycles, more instructions from that path enter the front end and back end. Then, eventually, the branch executes and the true outcome becomes known. At that exact moment, the CPU compares predicted direction versus actual direction, the predicted target versus actual target. If they match, great. Execution continues. If they do not match, recovery begins. The front-end redirect logic points fetch at the correct address. The younger instructions from the wrong path are squashed. Internal bookkeeping is repaired, and the machine starts filling with instructions from the correct path. A little later, the predictor also updates its internal state, so it can hopefully make a better guess next time. That last part matters too. Branch predictors are adaptive. They are not hard-coded rules like always taken. Modern predictors use history, patterns, and learned behavior to improve accuracy. So every misprediction is not just a penalty. It is also feedback. The CPU uses the result to train the predictor. Of course, some branches remain difficult to predict, especially branches driven by irregular input, data-dependent behavior, or highly variable control flow. For those branches, the CPU may keep suffering occasional flushes because the future is genuinely hard to guess. Now let's talk briefly about superscala out-of-order CPUs, because this is where the story becomes even more interesting. Modern CPUs do not just pipeline one instruction per cycle. They may fetch, decode, issue, and execute multiple instructions per cycle. That means by the time a branch resolves, there may be a large window of speculative instructions already in flight behind it. Not one or two, potentially dozens, sometimes more. So the cost of a misprediction is not just a couple wrong instructions. It can mean a large portion of the machine's working window was pointed in the wrong direction. This is why high-performance cores invest so much hardware into prediction. The better the prediction accuracy, the less often the machine has to throw away huge amounts of speculative work. And now we can answer the central question cleanly. How do CPUs flush the pipeline? They detect that a branch prediction was wrong. Once the branch resolves, they identify all younger instructions that entered the machine speculatively after that branch. They squash those instructions so they cannot retire or affect architectural state. They restore the front end to the correct instruction address, and they refill the pipeline from the real execution path. That is the mechanism, not magic, not a full reset, a controlled rollback of speculative work. If you remember only one mental picture from this video, make it this. The CPU is always trying to stay a few steps ahead of the program. Branch prediction lets it do that, but when the prediction is wrong, those extra steps were taken in the wrong direction. A pipeline flushes the CPU backing up to the branch, choosing the correct path and moving forward again. That's the cost of guessing. And that's also the price modern processors pay to be fast most of the time. That, because without speculation, they would be much slower. With speculation, they are usually right, occasionally wrong, and engineered to recover quickly. That balance, aggressive prediction plus precise recovery, is one of the defining ideas of modern CPU design. So next time you hear the phrase pipeline flush, think wrong path. Squash, speculative instructions. Redirect fetch, refill the machine, continue execution. That's what's happening under the hood. And once you understand that, branches stop looking like tiny control flow details in source code. They become what they really are, moments where the CPU has to bet on the future. And sometimes pay for being wrong.